Now that we know how to find critical chi-square values, we want to be able to use them to construct the confidence intervals that we're actually interested in. So we're going to find the confidence interval for population variance and the confidence interval for population standard deviation. Now notice these two are basically the same interval. All that happens is that the standard deviation has a square root in it because of course that's how you get rid of something being squared in algebra class. You learn that the inverse of squaring is to take the square root of it, i.e. to raise it to the 1/2 power. So when you take the square root, you're undoing the fact that it was squared in the first place. That's all. That means that variance is actually a little bit easier to work with because variance doesn't require the giant square root at the end, unlike standard deviation. Now, the requirements, because these are basically the same interval, are exactly the same. Namely that you have to have a random sample of size n, simple random sample of size n, and the population has to be normally distributed. Otherwise, you can't build the chi-square statistic, and if you can't build the chi-square statistic, you're in big trouble. Now notice there is no proviso for n greater than 30 or n times p times 1 minus p is greater than 10. None of that is there for these ones. Let me just show you the formula sheet from the exam really quickly. So when you look at the formula sheet for the exam, for proportions, we had n times p times 1 minus p greater than 10. That was the only way to prove that it was, quote, normal, end quote. Right? It's not really normal, but for our purposes, it'll do. Then down here, we had to have either it was given to us or a graph, or we had to have n greater than 30. But for standard deviation and variance, there is no option like that. You have to know that it's normally distributed, either given to you or in a graph, right? Those are your only options. I'll even add the little given graph thing there. So those are your two options. Given means just given to you, like I just wrote it for you in the problem. Now, remember that the chi-square critical values are with n minus 1 degrees of freedom. We just spent a whole page learning how to find those, so you're expected to be able to find them. And then here's some important information. Because the chi-square distribution is not symmetric, that means you can't do what we did for the other confidence intervals, namely find a point estimate and add and subtract a margin of error. That's not going to work for these because you don't have the symmetry that you had with the other distributions. So you're just going to have to find each of them by hand. And that's because the calculator won't do them either. So now it seems like, oh, that's terrible, terrible. However, this is actually the easier formula to put in. Once you know what the chi-square values are from the table, it's not actually that hard to find these intervals. And I'm going to prove it to you because we're going to do one together. Okay, so we have the graduate record examination, the GRE, is a test required for admission to many U.S. graduate schools. The Educational Testing Service, which produces the test, claims that student scores on the verbal reasoning portion of the GRE have a mean of 469 and a standard deviation of 120. Suppose a random sample of 10 students took the test and their scores are below. Now, our first job is to verify the requirements are necessary to make an interval for variance or standard deviation are met. And this is kind of easy because there's only 2 of them. I'll go back to the formula sheet that you'll have on hand at all times from this point on and see that, oh, the requirements are these 2 things. So I have to know that it's random sample and that it's normal. Well, I highlighted the random sample part for a reason, right? That gives us that the data are random. Done, right? It's given in the problem. And then we have to know that it's normal. There's no, bigger than 30, smaller than whatever, nothing like that. You just have to be able to look at it and know that it's normal. And since I didn't tell you anywhere up here that it was normal, I had to give you a graph right here to prove that it was normal. And it is, right? The graph at left shows that the data are normally distributed. So I should say yes. Nope. Right there. That's what the graph gives us. So now I want to go find the sample standard deviation and the sample variance. So let me go back to my calculator. I press Stat, Edit. Oh, here, let me make it bigger so you can see. There we go. And I typed in the data values here in L1. I cleared out the old and typed in the new. Then I want to hit Stat, Calculate, number 1. I'm going to go down to Calculate. My data are in list 1, L1. The frequency listed, just leave blank, and I'm going to go to Calculate. And what I'm in particular interested in is S. S is 105.446. I don't know how many decimal places they wanted. They didn't say. So I'm going to use 105.446 or 45. I'll use 446. Okay, now here's something. It's been a while. How do you find the variance from that? Well, remember the variance is s squared, right? So what we have to do is we have to take our value for s and we have to square it. Now you can type 105.446 and square it. That'll be moderately accurate. You'll get that number right there. But remember, we learned from way back in chapter 3 that there's another way to do this. If you hit VARS, V-A-R-S, it stands for variables. If you click that button, and you can see number 5 is statistics, which is the name of the course you are in right now if you're watching this video. So that's probably a good idea. So hit number 5. And then when you go to number 3, see SX, it actually knows the last standard deviation it found, which was 105.446 and some change. So if I hit SX and I hit the squared button over here and I hit enter, look at that. It actually gives it to me exactly, right? Beautiful. So that's what I'm going to type up. So it's 105.446 squared. Now, grant you, with this one, it kind of worked out to be the same thing for both of them because of the rounding, but sometimes you're going to be a little bit off with rounding, right, if you over round here. All right, now it wants us to construct a confidence interval for the population variance. So we're going to need to use formula and substitution and results. We're going to have to show all of that, the final result. I'm going to start off with just typing up the formula. So the formula says you use n minus 1 s squared and then chi-squared alpha over 2 and all this good stuff. And remember, you don't have to memorize that formula. It's right in your sheets right here. This is for variance, so it's this one. You do have to know variance is sigma squared, not sigma, which is standard deviation. All right, so there's our formula. Now we need to figure out a whole bunch of stuff on this. Well, we already figured out s. S is right here. And we figured out s squared. It's right there, so that's no trouble. What we do need to do is figure out the chi-square values. And to do that, we're going to need to figure out what alpha is and what alpha over 2 is and all that good stuff. So let's remind ourselves, since the confidence level is 0.95, that means that our alpha is 0.05 because they're complements of each other, right? Complements. Okay. All right, so now that we know that, let's see here. We need to be able to figure out alpha over 2. So alpha over 2 would be 0.025 because you take 0.05 and you cut it in half. And then the other one would be 1 minus alpha over 2. That'd be 1 minus 0.025. And that'd be 0.975. And so those are the columns that you're going to go to, right? Alpha over 2 and 1 minus alpha over 2. Now your row is your degrees of freedom. And since our sample size was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then degrees of freedom is 9 because you take 10, take away 1. There we have it. All right, so now that I know the columns I'm going to and the row I'm going to go grab the table and find these values. I'm going to go back to my appendix sheet here. All right, and I wanted the 0.975 and 0.025. They're right in the middle. My degrees of freedom was 9. So I want 2.700 and 19.023. Those are the two critical values. One of them is the one on the right, the 19.023, and one is the one on the left, the 2.700. Now that gives me the values that I'm going to plug into the bottom of my lovely, lovely formula here. So I have 10 take away 1 times 105.466 squared divided by 19.023 or 2 and 2.7 respectively. The numerators, interestingly enough, are exactly the same for both of them, right? Now, if you wanted to, if you don't want to write 105.446 squared, you could actually write 1 is the number we found up above. 11118.9. That works, right? Because that is the s squared we found. So you could actually write it as 105.446 squared, or you can write it as the s squared value if you find it ahead of time. It doesn't matter either or. I'm going to leave them both up because they're both valid. Now we just have to go type those into a calculator. Okay, so I think what I'll do is I'll do the numerator part first. So remember, it was 9 times 11118.9. Divide that by 19.023. Okay, so that's how to do that. Now, if you want to do it with the squared part, that's fine. You can say 9 times 105.446 squared, divide by, close that parentheses, divide by 19.023. It doesn't technically need a parentheses, but it's fine. Now, they're a tiny bit off from each other, right? But that's why you show all your work, because I will accept either one of these answers as long as you show me all the work. So I would say it's 5260.48 because I'm going to use the top one. That's actually more accurate. But again, if you use the bottom one and just show all your work, I'll accept that as well. And then before I go do I'm going to go do the other one before I go anywhere else. So it's the same thing. I want to take parentheses 9 times 1118.9. And again, you don't really need the parentheses, but I like it because it just kind of helps organize what we're doing and when. So that's the end of that numerator. I'm going to divide it by 2.700 for the other one. And that gets me 37063. Now, if you had used 9 times 105.446 squared, close parentheses, divided by 2.700, you'd end up with that number. Now, they're very close, they're very similar, but that's why you show all your work, because I would accept either one of these numbers. I'm going to put into the notes the more accurate one, which is that one. Well, now that we know how to find the one for the variance, what if they had asked us to do the standard deviation instead? Well, the answer is you would have done the exact same thing. All these steps would have been there. It's just you would not have circled this as your result, right? You would have gone one step further, which is what we're about to do. So if they ask for standard deviation, all you do is find the variance like we just did, and then just take the square root of it. Remember, because standard deviation is the square root of the variance. So we would take the square root of both numbers. So let me prove it to you. So if I take the square root of 5260.47942, that was the number we actually got, I get 72.529. And then if I take the square root of second square root 37063, I get 192.518. There we have it, the two numbers. So that's all you do. It's simple as that. Now, if they had asked you from the start to do that, you still would have done the exact same steps. The way I do it when they ask me to find standard deviation is I find the one for variance first because it's easier. Variance is actually simpler than standard deviation. And then I just take the square root of my answer and I'm done. All right, now let's stop right here because the next bits take a little bit longer and I'll come right back for those. Actually, I'm going to go on. So we want to interpret the interval for the population standard deviation in the context of the situation. Well, this was a 95% confidence interval. So we're 95% confident that the true proportion standard deviation of all GRE verbal scores, which is sigma, is somewhere between the two numbers that we found, 72.529 and 192.518. You would use units if appropriate, which this one doesn't have any units, so there's no units to use. It's points out of a test, so it's not even a percent or anything. Right, and that true proportion of all GRE verbal scores, I'm getting that from up here where it says, you know, the produces a claim which tests that the student's verbal reasoning scores are here, blah, blah, blah. And then they claim that their standard deviation is 120 or whatever. Okay, so next. Now, the margin of error cannot be found by doing what we've done before. So up until this point, we could find a margin of error based off of half the width of that formula. And the reason you can't is because this distribution is not symmetric. So that means that since it's skewed right, it's not going to be perfectly in the center. The point estimate will not be in the center like it used to be. Let me draw you a picture. There, I drew a lovely little picture for you, if I do say myself. All right, so S is in the center. S is your sample standard deviation. That's your point estimate, right? It's still your point estimate, even though it's not smack dab in the center, which it's not. It's over on the left side of it, and that's because this distribution is skewed right. Because of that, you're going to have a longer tail on this right-hand side, and that's always going to happen for chi-square values, right? You're never going to be able to take the point estimate plus or minus the margin of error like you can for z's and t's. And that's because the chi-square distribution isn't symmetric like the z and the t, right? That's why for z intervals and t intervals, you can do that. For proportions and means, you're totally fine. Mean plus or minus the error, good. Or proportion plus or minus the error. But for chi-square ones, it won't work. And it's because the point estimate is always a little bit to the left of the center. Actually, sometimes quite a bit to the left of the center. Now, the company claims that the standard GRE of all verbal scores was 70. That means I'm going to have to change the original problem. Sorry about that. I should have said 70 up here instead of 120. So there it is. I made it 70. So they're claiming it's 70. And our question is, does the interval support or contradict that claim? And the answer is it contradicts it because 70 is below our interval, right? Since 70 is below our interval, right? Our interval stops at 72.529. We contradict. Just on a little side note, a contradict or support question is not a yes or no question. You have to choose one, support or contradict, and then you have to explain yourself. Now, if they had made a different claim, our interval could have supported them. If they had claimed it was more than 70, our interval would support that because our interval is above 70. If they had claimed it was 120, which is actually what they really did claim, so if they really did claim those things, then the interval would support them because 120 is inside that interval, right? But claiming 70 when 70 is not in our interval does not support that. If they had claimed it was less than 120, our interval would contradict that because our interval is not all less than 120. We have a whole bunch of stuff over here that's above 120. Which means it's going to be very important to us what the claims are that are made because a small change in the wording, if they claim it is 70, we contradict. But if they claim greater than 70, we support. Our interval supports that because our whole interval is above 70. Right? If they claimed less than 120, no good because our interval is not less than 120. If they claim less than 200, sure, our interval would support. Right? Matter of fact, let me type that one up. And this obviously means that wording is very important to us. That English language thing that I've been getting you guys on about all semester, you have to pay close attention to what is being claimed and whether your interval supports or contradicts that based on the data that you have. All right, we're all done with that video. I'll see you back here for the next.